Welcome to The Explainer. Today, we're going to jump right into a concept that's, well, it's pretty fundamental to modern computing. How in the world do programs manage to do multiple things at the exact same time? We're talking about Pthreads. So, here's the plan. We're going to walk through the whole thing, from the very basic idea of what a thread even is, all the way to the nitty-gritty tools you need to make them all work together without causing chaos. All right, first things first. Let's get a real solid handle on what we mean by a thread. You hear this word thrown around all the time, right? Especially when people talk about processors with multiple cores. But what does it actually mean when you're writing the code? The source material here really nails it with a simple definition. Let's just forget about all the super low-level complex operating system stuff for a minute. The best way to think about it is just as a mini program, a self-contained chunk of work that's running inside of your main program. And honestly, this is the perfect way to think about it. Imagine if a head chef had to do everything one step at a time. First, chop all the vegetables. Then, saute everything. Then, plate all the dishes. It would take forever. Instead, you give the chopping job to a team of assistant chefs. They all work in parallel at the same time. And the result? The whole meal gets done way, way faster. That is the promise of using threads. Now, what's really fascinating is the backstory of how this amazing idea actually became practical for developers everywhere. Because back in the day, getting all those assistant chefs to coordinate, that was not so simple. Let's look at how a standard finally brought order to the chaos. In the early days, it was a total mess. It was like trying to run a kitchen where every single brand of oven and stove had completely different dials and instructions. A recipe that worked on one wouldn't work on another. For developers, it was a nightmare. You'd write this brilliant, efficient code for one system, and it would be completely useless on another. And that really gets to the heart of it. The entire developer community realized, hey, to really make this parallel computing thing work, we need a universal language. They needed one single, standard way to create and manage threads that everybody, all the hardware makers, all the operating systems could agree to use. So that solution finally arrived in 1995. It was called POSIX, the Portable Operating System Interface, and it gave us the Pthreads standard that is still the foundation for so much today. It means you can write your code once and be pretty darn confident it's going to run on all sorts of different systems. Okay, so we've got the standard, but how do you actually use it? How do you tell your program, hey, I need you to spin up one of those assistant chefs right now? Well, let's look at the core function that makes it all happen. This right here is the magic wand, pthread create. This is the command. It's the function call where you, the programmer, tell the operating system, hey, I need you to launch a new, independent task for me right now. But to do its job, it needs you to give it 4 specific pieces of information. And each part here has a really important job. First, you need a way to keep track of the thread, to identify it. Then you can give it some special attributes. We'll talk more about those later. And then the 2 big ones. You have to tell it what function to run, what is its job, and finally, what data, one single piece of information, should it work on. Now, this is where it gets real. This single line of code, pulled right from our source material, is the moment of creation. It's launching a new thread that's going to run a function called print_hello. This is basically the hello world of parallel programming. It's that very first crucial step to making your program do more than one thing at a time. Okay, but wait a second. That pthread_create function, it only lets you pass one single argument. What if your thread needs more than that? What if your assistant chef needs to know the vegetable, the cutting style, and the bowl to put it in? This is a huge pitfall, a place where tons of developers get tripped up. So the pros, the people who do this for a living, they have a really smart and safe way to handle this. You create a custom container, it's called a struct, and you just bundle everything the thread needs into that one container. An ID, a message, a number, whatever. Then, and this is the critical part, you make a fresh, unique copy of that container for every single thread you launch. So here's the bottom line. The safe way is to give each thread its own private briefcase of data. It's theirs, it's personal, and no one else is going to mess with it. The unsafe way? That's like telling all your threads to look at the same sticky note on your monitor. A sticky note that you are constantly erasing and rewriting. By the time a thread gets around to reading it, the information could be totally wrong, and that leads to some really bizarre and hard-to-find bugs. Okay, so we've successfully created our threads, and we've safely given them each their own little briefcase of data. They're off and running their tasks. But how does our main program, our head chef, know when they're actually finished? You can't start making the sauce until the vegetables are chopped, right? So, the first thing you have to understand is that when you create a thread, it exists in one of two states. It's either joinable or it's detached, and this state defines the entire relationship. It determines how, or even if, your main program is allowed to check in on it after it's been launched. Let's go back to our kitchen for a second. Joining is basically the head chef looking at an assistant and saying, okay, your job is to chop all these onions. I am going to stand right here and wait, and I'm not doing anything else until you come back and tell me you are completely finished. That pause, that intentional wait, is synchronization. Now, the POSIX standard gives us a whole toolkit for this stuff. But honestly, the one you're going to hear about the most is pthread join. That is the specific command that tells your program, pause, stop right here, and wait for that specific thread to finish its job. The other commands are helpers, letting you manage that joinable or detached state. So it all boils down to this, and it's a really great rule of thumb from the source material. Just be clear about what you want to do. If you know you're going to need a result back from a thread, you have to wait for it, so create it as joinable. But if it's just a fire and forget kind of task, create it as detached. That actually helps the operating system clean up and reclaim resources much more efficiently. So what's the big takeaway here? Pthreads are this incredibly powerful standard tool that lets you tap into the real power of modern processors. But, and this is a big but, with that power comes a huge need for discipline. You have to be so careful and so deliberate about how you handle data and how you coordinate timing. Otherwise, you end up with a chaotic kitchen instead of a well-oiled machine. Think about it. Every single time you use an app where a loading bar is moving, but you can still click on other buttons, or when you're watching a video and a file is downloading in the background, you are seeing threads in action. It's happening all around you, all the time. We'll leave you with that thought. Thanks for joining us for this explainer.